Hello everyone, my name is Peiyuan, come from KTH, Department of Material Science and Engineering. The title of the presentation is CFD in Process Metallurgy, so I come from engineering field. In the presentation, I will have a general introduction about our department, and then I will give an overview about our research during metal production. This is a general picture about KTH's our school. We have 12,000 full-time students, 1,800 PhD students, and around 3,600 employees. So the Department of Material Science and Engineering, we have 100 employees and 70 PhD students. The research in our department covers from the process, material structure, and material properties. Our group, Applied Process Metallurgy, belongs to a division of process. The group leader is Professor Peiyuan, and in our group we have one professor, one emeritus professor, two affiliated professors, one associate professor, one assistant professor, and 4 researchers, and 15 PhD students. So these 5 senior researchers carry out the CFD study during process metallurgy. So in the following, I will give a general introduction about the research. In our group, we do generally in the 3 kinds of research field. One is the metal refining. This is a very complex process because the temperature is very high, around 1,500 degrees centigrade. Sometimes we don't know what happens inside the furnace because it is too high temperature. So this is a multi-phase flow process coupled with the chemical reaction. Another concern is about clean steel because there are a lot of or clean metal, because there are a lot of non-metallic inclusions in the metal. This kind of inclusions is not good for the quality of the metal product. And also it is dangerous for the production process. In the last, I will see something about metal casting. Recently, we developed some new methods for the metal casting technology, that is swirling flow metal casting technology. So I will give a general picture about that also. First, I want to talk about the metal refining. This process is coupled the kinetic and the thermodynamic reactions. The aim is for the desulfurization, decarburization, and the degassing. This picture generally shows the process of this kind of metal refining process. So we can see that here we have the bubble injection. The bubble will float up, and the bubble will broken, and then there is metal splashes. Maybe go to the top slag. If too much metal go to the top slag, then the metal will lose. So in the process, we have the bubble flow, we have liquid metal, we have molten slag, and we also have interface chemical reaction. How to model this process? We using the following method. First, we use a multi-phase Euler scheme to simulate the 3-phase flow phenomena. And for the interface reaction part, we need the help from the thermodynamics. For the reaction part, we need to know the activity of each element. We need to know the transport of each element. And we also need to know the dynamic equilibrium. Dynamic equilibrium, this part we need to calculate from the thermodynamic software. This part we normally use the thermocalc, which is developed at our department by some researchers. So by couple the CFD simulation and the thermodynamics, we can realize a dynamic simulation about the refining process. This picture shows the 3-phase flow. So from here we can see that there are different density because the top is slag, and the bottom is metal. There is some mixing region where the interface reaction happens. And here shows some result about the sulfur content in metal over time. You can see that after 15 minutes, the sulfur content in the metal becomes very low. Another important thing is that we try to reduce the amount of hydrogen in metal, because hydrogen is very dangerous for the metal quality. So we also use the previously described model. In here, the process is, this is the dissolved hydrogen in metal. This is the hydrogen gas in gas bubble, because we need to blow argon from the bottom. Yeah, by combine the CFD and the thermodynamics, we can simulate the refining process to remove the hydrogen in the metal. This is for the decarburization process. In the real production, there is a top oxygen blowing, which provide the oxygen to react with the carbon. There is bottom gas blowing. This is mainly for the stirring, for the mixing, for the transport. This picture shows in the middle shows the production in the production plant. We can see that it is, we don't know what happens inside. So simulation is a method to give an idea about the process optimization. And we couple the CFD model with thermodynamics. We simulate the decarburization process. So this figure shows the bottom figure shows after 5 seconds the carbon concentration in the metal bath. Yeah, another topic is about the inclusions in metal. Because as I mentioned previously, inclusion is not good for the metal quality. So we try to remove all the inclusions in the metal. If we can, then yeah, that is good. But if not, then the inclusion can lead to other problems, like the inclusion deposition on the ceramic walls. That will close the nozzle, and we must stop after it is closed. So we use electrolytic extraction. We get the inclusion in metal sample. We can see that it is very complex, and there are actually has a huge number of inclusions in the metal sample. It is 10 order 7 to 9, so it is a large amount. And the size distribution we can see from here. Generally, it is in micro level, 20 micro, 30 micro, in that level. So it is very small. So in order to remove it in the real production, we generally inject argon gas. So here shows the, sorry. Yeah, one gas bubble float up. We can see that the bubble shape changes over time. So this kind of simulation takes quite a long time. Here we only simulate one bubble. If we simulate the amount of gas as the production, then it maybe we need high performance computing. So in this kind of project, maybe we can cooperate with Johan Janssen to do that. Yeah, we can see that when the bubble float up, the inclusions also go up. We want to make inclusion go up, because if it go up, then if it touch the top slag, then it has possibility to be removed. Yeah, this figure shows how the inclusion remove. Professor Keiji Nakajima and Professor Peiyuan, they developed the mathematical model. Here shows how the individual inclusion go to the top slag. because when the inclusion go to the interface, it may go to the slag phase, or it may go back to the metal. So we need a model to do this. This is a micro model. By considering the forces acting on each micro inclusion. So it is, for sure, it is very difficult to in CFD simulation to include this model, because it is in micro level and it is too difficult. Another concern is about the deposition of inclusions. We can see that the picture, this is a nodal closing. After some production time, then the inclusion will stick on the nodal wall, and it will close the nodal path, the flow path. The reason is that these inclusions in metal, normally it is not wetted by the metal. So when it go close to the wall, then it tends to stay there because of the interfacial force. Yeah, in order to describe the process, we need to think about the mechanism of the inclusion transport to the wall. So we can see that here is the turbulent region, and go inside there are some layers, and finally it is a laminar layer. And this inclusion transport process is closely related with the near-wall turbulence structure. So in order to describe the inclusion transport to the wall, we need to have a good solution on the turbulence near the wall. So we need a very fine grid. This picture shows the DNS simulation. We can see it is a blue line. The red line is the RFM simulation. And the green line is the K-epsilon. So we can see that K-epsilon model cannot capture the turbulent fluctuation in boundary layer. So you use the K-epsilon model, for sure it is difficult to describe this kind of transport. However, if we use DNS simulation, then it needs quite much computation time, or even impossible for high Reynolds number. Currently, we use another method to simulate the transport. That is a Euler particle deposition model. This model is firstly developed by Professor Sten Tore Johansen from Sintef in Norway. So I will generally describe this model, how it works. In this model, the only input is the friction velocity. So we can use we can use wall function to estimate the friction velocity at the wall. Then input the friction velocity, then we can get the general picture of the transport. And then in this model, it is a Euler method. Then it means we do not consider individual particle. Instead, we consider the particle as a concentration. So this is the concentration transport of particles. Yeah, we write it in the dimensionless form. Then we can see that this picture is the flux. Here is the Brownian diffusion. This is the turbulent added diffusivity. And another important thing is the particle convective velocity. At this velocity, we need to solve the particle transport momentum equation. These two. And there are two important parameters in the model. One is the added diffusivity. Another is the particle mean square velocity. Here we need an assumption. We assume it is equal to the fluid property. And then this kind of property can find from the literature. So therefore, the only input for the model is the friction velocity. And then we get some input from the literature. We don't need to solve the boundary layer again. Then we can know the inclusion transport flux. For the model validation, because directly validate the model in the metal flow is too difficult because the temperature is so high. This result is the gas, the liquid droplet in turbulent gas flow. So we can see that we can see that the model prediction and the experiment result actually fit very well. So we use this way to simplify the particle transport in the boundary layer, because this we can save a lot of calculation time. Okay, then we use this method to describe the inclusion deposition in metal flow. Here is the metal inlet. Here is the tan dish. Here is the ethylene where the metal go out from here and then go to the mold for the solidify. In the ethylene part, there are a lot of problem about the nodal clogging, as I previously showed the picture. So we use the Euler deposition model. We calculate the deposition rate along the wall surface. Another application of the model is for the inclusion removal, because the top, here is the molten metal flow, and at the top there is a slag. So we want to know the flux of the inclusion from metal to slag. So we use the Euler deposition model to predict how much inclusion can go during the production process. Yeah, swirling flow metal casting. This is recently we do some work about this. Why we do this? Because in a plant trial we find that swirling flow is very helpful for the quality. That can be easily seen from from this figure. We can see that in the conventional nozzle, this is a swirling flow nozzle. We can see that the surface quality is much improved by a swirling flow. But the problem is how to produce a swirl flow in a cost-saving way. Here is our design about the turbo swirl, which is used in the ingot casting. Here we can see that the metal flow along the path and go to the mold where solidification will happen. So we input the turbo swirl here, then the flow pattern will change. You can see that this is no swirl flow. This is swirl flow. Why we want it? Because from this figure we can see that when no swirl flow, there is the hump. The hump is very high. That means it is imposed to the air. The oxidation can be happen. So that is not good during metal solidification. So when we're using a swirl flow, we can see that the heat is not so high, and actually we get a very stable flow in the mold. In this way, we try to improve the steel quality. This is another application. Here there is electromagnetic stirring outside of the nozzle. Here there is a top slag where inclusion can be removed. Here is the mold where solidification happens. So we use the CFD model, input the magnetic force to simulate this process. And here shows some result. We can see that it is quite different. Why? Because we can see that here the black line is no swirl flow. That means the penetration depth is very deep into the mold. That is not good for the inclusion removal. And this line shows the velocity with the swirl flow. We can see that in the vertical direction, the velocity is much reduced. This figure shows the flow pattern in the mold. We can see that for no swirl flow, there is no tangential velocity. With the swirl flow, there is tangential velocity. Why the tangential velocity is helpful? Because we can see from here the temperature distribution. Temperature distribution with the swirl flow is much uniform compared with no swirl flow. Yeah. For the swirl flow, another aim is that we want to design some simple way to produce swirl flow, because electromagnetic stirring, it needs equipment investment and electricity cost. Here is a simple design. We can see that normally here is a conventional tan dish. So we add a cylinder tan dish. Where the cylinder tan dish, there is a tangential inlet here, and here is the outlet. We can see that a swirling flow is produced. So this is a very simple way by using the steel flow potential. And currently we are doing this kind of work for more investigation. in a swirling flow, because the particle density is lighter than the molten steel, if here is a particle, then there is a centripetal force. Then the particle will move towards the center. After particle move towards the center, then its possibility to touch the wall will reduce. So from this figure, we can see that for aluminum inclusion, the number of inclusion touch the wall reduced a lot with the increase of the inclusion size. Yeah, generally, this is some of the research currently we are doing. And we have planned to cooperate with Johan using Phoenix to maybe to carry out some complex computing, yeah, in future, especially the bubble behavior in the metal. Yeah. Thank you.